Okay, hello everyone. Another video snippet on calculating the value of pi. And this time we're getting a bit closer to the classic method, which is based on inscribing polygons with an increasing number of sides inside a circle, which for simplicity we choose to have a radius of 1. But in this first example, let's consider this equilateral triangle, the green one. And to calculate the area of this equilateral triangle, we calculate the area of the red triangle instead, which is a right triangle with a hypotenuse equal to 1. Given this, then to calculate the area, we must multiply the two legs and divide by 2. So we can derive the longer leg from the laws of trigonometry by measuring the hypotenuse times the sine of the 60-degree angle. And let's say, in this case, since the hypotenuse is 1, we can write sine of 60 degrees directly. The same thing for the shorter leg, cosine of 60 degrees. So we have this little formula for the area of the red triangle, 1/2 sine of 60 cosine of 60. Now, instead of solving and going directly to the numerical result, let's observe that with another trigonometry formula, we can write this expression as 1/4 sine of 120 degrees. So we observe again that 120 degrees is nothing but the full angle, therefore expressed in sexagesimal degrees, 360 degrees divided by n. And so for the red triangle, we have an area equal to 1/4 sine of 360 degrees divided by n. From the construction, it can be seen that the green triangle is obtained by 6 times the area of the red triangle, therefore 6 times the area of the red triangle. But here too, we notice, let's bring in the number of sides, which is 3, and so we write it as 2 times n times the area of the red triangle. So in the end, we have this little formula, 1/2 that multiplies n that multiplies sine of 360 divided by n. This formula gives us the area of this triangle, the green one, obviously. If we replicate this formula and we go to calculate it for the square, we see that we can replicate the same reasoning, and in the end, we get exactly the same formula. What has changed? The value of n, the number of sides, has changed. This time we have n equal to 4. We will have 1/2 times n times the sine of 360 divided by n. So this formula is valid for almost all inscribed polygons, and we can see what happens if we let n tend to infinity in this formula. Here, the computer and the Python language can be useful to us because we use the very simple code that is written here at the bottom to obtain, let's say, an approximation of this limit. One thing to note is this. In the formula, we have here 2 times mt. Mt is the abbreviation for math, times pi, which stands for pi itself. So someone might rightly notice, why are we using pi to calculate pi? There is a contradiction. Actually, the problem is it's quite simple. It's the fact that this library uses degrees in radians, but nothing would stop you from using a library with sexagesimal degrees. Now let's see if the approximation of the limit works out with this possibility. So I've already loaded the code. I've already done a test, as you can see. I also wrote here to use sexagesimal degrees. Here it is. Let's start the approximation, and you can see that we are already getting close to the actual value of pi. So this is a simple demonstration of how one can obtain this fundamental value of mathematics with very simple operations and with the use, obviously, also of the computer, which makes the calculation easier for us. All right? Greetings to everyone. Until next time.